Welcome. This is lecture 5, Ensemble methods. We will do it in 3 parts today again. We will first look into what is the basic idea of ensemble learning. And this basic idea is very, very simple, but we will go on from there to see why is it a good idea? What makes it work in practice so well? Then we will look into a specific example from practice where ensembles helped achieve a lot and also not. And we will see both aspects in the practice of using ensembles. And then we'll look into a specific algorithm. That's our algorithm for today, adaptive boosting, AdaBoost. That was basically, now we have the deep learning height. Before that, we had the support vector machine height. Before that, we had the AdaBoost height, if you want. You can see it like that. Good. Objectives for today. You should remember when ensembles should work and when they should not work. So under which conditions they are a good thing to try. And you should have arguments present. You should be able to present arguments how and why these things work in practice. So what's the reason behind it that it works so well? And you should be able to apply the truth. The lecture will tell you the details of the method, which are remarkably simple, and the lab will tell you how to use it. Again, using scikit-learn, you don't have to implement the algorithm yourself. You can just use library functions and try it in the setting of email spam classification. You can even put in later your own emails and see if you can find system you receive. Good. Let's start with meta-learning. Meta-learning is a term that I really like to give to ensemble methods. Why? Because when we are thinking about ensembles, like sets of classifiers that collectively achieve the goal, or regression methods, not just classifiers, then we're talking about a method, the ensemble building method, that is not operating as an algorithm on the data itself. That is what a machine learning algorithm does. But the ensemble method is operating on other machine learning methods. So it's a level higher. This is why I think the term meta-learning is very good for that. And you could read it in that regard quite frequently a couple of years ago, until a new theme emerged called learning to learn. Has anybody heard of learning to learn yet? You, not too many. Learning to learn is a new field, more or at least currently on the rise, a field of study where it's about, can we automatize machine learning fully? As you have already realized in the sort of machine learning we are doing, the machine is learning some part of the problem, but we as a human still have to contribute a lot. We have to select the hypothesis space and how we search it, so basically the learning algorithm. We have to create the features. We have to tune the hyperparameters of the method. So in the end, yes, the machine does some part of the learning, but it still needs some smartness from us. Learning to learn, or automated machine learning, tries to get rid of that part as well, at least for simple problems, where you just have a bunch of data, you throw it into a machine, and out comes a model that can do the trick. And you don't have to select anything, you don't have to prepare anything, you don't have to tune anything. And that usually goes by the name learning to learn. I just created today a slide and put it into the appendix that is quite vast today. I think you have more slides in the appendix today than in the lecture. So there's lots of material if you like to delve into it. Also learning to learn, a specific system in a one-pager. If you want to know more, read the blog post from the Berkeley guys. They did and do some great work on that. And this is sometimes also called meta-learning. So nowadays these terms are somehow mixed. If you say meta-learning to a colleague today, he or she will probably think you're talking about learning to learn. Today we're talking about meta-learning in the sense of ensembles. So what's an ensemble? An ensemble is the idea of combining multiple, and I say here classifiers, but the same holds true for regression for the whole lecture today, but we will talk about classifiers. So it's about combining multiple complementary classifiers so that the ensemble, the combination of those, is better than each single one. The magic word here is complementary. This idea works great if the classifier is actually different. If they have some difference in it, if they complement each other. If they don't, it will not get better. Right? That's the same idea as what you have in human resources. When you have a team of all the same people, it usually underperforms in comparison with a team that is very diverse. The people have different mindsets, different backgrounds, different ideas. That usually sparks creativity in human teams. Here, it hopefully boosts our performance. How do we do that? We build the different experts, we let them vote. And in the end, if it's a binary classification, we can just say, okay, we take the majority vote. And that's it. So this is the whole idea in a nutshell. And actually, if we talk about classifiers, it's as general as this. It doesn't mean you need to combine several support vector machines, but you cannot combine a support vector machine with some other element. Yes, you can. If the things are complementary, you can combine them. The method is general enough for that, even if you usually don't use it in that way. But you could. What are the pros and cons? It is very effective in practice. It actually just gets better with everything you add, as long as they are complementary. There are a lot of papers from the 90s about theoretical work, why it is better and how much better actually it is. So there are upper and lower bounds on what you can achieve with an ensemble, and these theoretical guarantees are actually really good. So it's not just practically good, there's reasoning behind that. And it's actually easy to implement. If you think about that, build several things and then let them vote, it's basically just a loop. You just have to implement that formula. Take your classification, maybe multiply it with a weight between 0 and 1 that specifies how much you trust this specific one in comparison with another one. Sum it all up, and if it's binary classification, you can just take, and the label convention we had last time, negative label -1, positive class +1, you can just take the sign of the final outcome. That's your classifier. A loop, and checking if it's positive. So it's super simple to implement. Negative. And maybe you can comment on that. Why are ensembles less transparent? And why should we care? Yes?
It's not clear which part of the solution or which method contributes which part of the solution.
It's not clear which part contributes to the solution. Yes, exactly. Yes?
Can we not analyze the weights we use?
We cannot so well analyze parameters inside like weights. Yes, exactly. These ones. We have weights here. They usually come out of the ensemble learning method. They somehow contribute to what part contributed what, in the sense of which classifier contributed how much. But maybe this can also go deeper. Which part in that classifier. Overall, it just gets more complex. If a single model has a certain complexity, having 10 such models or 100 such models makes the complexity 100-fold. If transparency is about managing the complexity, then of course a more complex model is less transparent, in the sense less easy to comprehend. Why should we care about it's not compact? Of course, the same argument. It's not compact because we have 100 times the same classifier, the same number of weights, I don't know, whatever. But why do we care about compactness? Think back on, yes?
Doing inference is more computationally, it costs more to do inference with a not so compact model?
Doing inference is computationally more costly if the model is bigger. Yes, for sure. That's a good practical reason. There's also a theoretical reason, and we talked about that in lecture 3. Can you remember William of Ockham and his famous theorem called Occam's razor today? Occam's razor is one of the foundational building blocks on which modern machine learning lasts, and it basically says you should prefer a simple model because simple is good. And if we have a not compact model, if we have a model that has unnecessary many parameters, even if it's much better, it might have redundancy in it that in itself is not good. So usually we strive for a simple model, for a compact model. Compactness is one way to measure simplicity. So here we have Occam's razor as a counter-argument, and here we have the transparency or the interpretability argument that are against ensembles. But we have lots of good stuff on the pro side, so let's delve into that and see what we can do on it. What's the formal problem description? We have big T binary classification hypotheses, and yes, it of course can be extended to multi-class and to regression. We call it H1 up to HT. And what we want to do is find a combination of these classifiers, a combined classifier, with better performance. What does it mean? Actually, it means to find these weights between 0 and 1. And in the most simple case, they all have an equal weight. We will actually see how let's just do that. So far, so good. Let's look into some reasonings why this actually should work. Let's start with the intuitive thoughts. Diversity, we already talked about it, is a thing that even in human collaboration we nowadays think is a good thing. And it's basically exactly the same thing what we hope for when we use machine learning methods and diverse methods, like methods, how did we call it here, complement each other. Think about lecture 1 and the topic of inductive bias. If we take completely different classifiers, maybe even different modeling paradigms behind them, like different algorithms that build the models, they will likely have a different inductive bias. So they will look for different things in the data, for different kinds of patterns. So even if they have roughly the same base performance, if they look at different things, it might really be that one time this classifier is wrong, but this one is right. If I have more than 2, if I have a lot of them, and a usual ensemble has not just 10 members, but can have hundreds of them, then we should think that the combination of all this diverse knowledge should be a good thing overall. The second point is, and this is something we also talked about in lecture 3, it's difficult to know which of the many models we might have built during our experimentation is actually the best one. We talked at length about that it's difficult to find out which one is the best, and even if we found a winner, we are not completely sure if this is actually really the best or just a numerical issue. So we might have in the end several models built that all perform differently, but on average roughly the same. So why not use all this different knowledge that has been collected and combined? So that's the intuition. To just give you a feeling for how good that should work, let's make a theoretical example. And it's theoretical because we assume complete, utter independence amongst all our classifiers, which is in practice not the case. We talk about diversity, we want to have them have different views, not to be exactly equal, but complete independence is something that's difficult to achieve in practice usually. So let's discuss that theoretical example. Let's say we have 25 binary classifiers. Each of them has an error rate of roughly 30%. So they are 70% accurate, 25 of them. We assume they're independent, and what we can do then is we can calculate, just by using basic laws of probability, how accurate will be a majority voting ensemble of these 25 classifiers. So we can calculate what is the probability that a certain number out of our 25 classifiers are wrong in the end. This just follows a binomial distribution. This is the equation for it, which can be looked up somewhere, not a big magic. And because we assume independence, having 13 classifiers that are wrong have a certain probability. I think 40 has a certain probability, and so on until 25, because they are independent and can sum it up to arrive at the final probability. So our final classifier will have, in that setup, will have an error of only 6%. So out of 25 mediocre classifiers, 30% error. Just by combining them, we get a theoretical maximum error of the final combination of only 6%. And we basically get it for free. That's the power you basically have when using Ensemble. In practice, it will maybe not work as well as this. This is quite amazing, but this is basically what we're at. Getting better, getting a very good classifier out of only good ones. So, this is cool. And you see the complete derivation in the appendix if you're wondering. So, some more arguments. Why are ensembles good? There's a statistical argument. Given only the sample of data we can train on, the training data, which is not the whole data, we will probably be unable to identify the true function completely, like 100%. We will, with our estimations, reach points that are somehow close to the true function f, but we will not directly go there, not because we cannot find it, but because we do not see all the data, and thus it's impossible to find it. So when we start from different data sets, for example, we may arrive at different hypotheses that look optimal from the point of the limited sample, but are non-optimal from the point of the whole set of data points that we haven't observed. Just imagine that image. I think that drives the point home. We have these different hypotheses we build. We are not sure which one is the true one. Just imagine the true one would be in the middle of them. Then averaging over the 4 ones we have found is a good idea. It brings us closer than we could statistically estimate. Of course, it could also diverge, but this shows why it could be a good idea. Another argument is computationally. We saw when we looked into the algorithms that do gradient descent on some error surface that it can easily happen that we get stuck in a local minimum. If we do so, we have to keep a suboptimal model. And we start a little bit from a different place, we run to a different local minimum. If we average over them, we might again be closer to the thing we're actually looking for. And the final thing, this one is the coolest. It's a representational thing. When you choose, you look at your data and you choose a specific machine learning algorithm to build a model. What you usually do then, you choose a hypothesis space that can host a specific form of hypothesis. Do you remember from, maybe it's interesting to bring that up again here. Yeah. You remember that slide? With the same data set, lots of models with the same performance here and here and here, all the same performance, but the hypotheses look completely different in their build. Because this thing, a random forest or a decision tree, they can only build rectangular surfaces. The nearest neighbor method is not bound to just rectangular stuff. So when you select a decision tree, you're bound to things that are rectangular. So if your decision surface that you actually want is curved and you're bound to rectangular stuff, you can only get so close to the true function because you're limited by the hypothesis space you have chosen. But by combining these, you can basically get outside of your original hypothesis space. Combining lots of rectangular things gives you something that can look like anything. You basically can digitize a curve or whatever. So that's really powerful. 3 arguments why ensemble building enhances your capabilities, or the capabilities of your classifier. Last thing, We talked about bias and variance in machine learning also in lecture 3 as a way to see, at least for regression algorithms, how our error that we observe is the result of 3 different components. We have the noise, the error we cannot remove because there's noise in the system, on our labels, on our measurements, on our data. We have a bias component where we are systematically off by the choice of our hypothesis space, for example. We've chosen something that can only make rectangular surfaces, but we need a curve. So we have a bias component, and we have a variance component that is due to the specific sample we are training and testing on, and if you would choose a different sample, it would look a little bit different. And we also talked about that in regression, it really looks like that, a sum of these 3 terms. It turns out that ensembles are a great thing because they don't do anything to the bias. The bias just stays the same. Just see if I'm... Yeah, exactly, here it is, sorry. I thought it's on the slide and I didn't see it on the first one. What you usually have is, if you build an ensemble, combine the classifiers, do majority vote, you do not change the bias of the method, the bias part of the error, but you reduce strongly the variance. So what you're doing, even if all your classifiers are at the same error rate, you're reducing one component of the error rate. And that means you can only get better. If your classifiers are diverse, you cannot do harm by adding more. Yes, of course, regarding the 2 cons we had on the first slide, it gets less interpretable, it gets less compact. You can do harm by adding more. But error-wise, you can only improve. That's a great news. Let's do a first example of an ensemble building method. It's a bagging method. Bagging is a name for it. Bootstrap aggregation. It's from Leo Breimann again. I think we encountered Breimann already 1 or 2 times in the course, and he will show up again. Quite the famous guy with great results, and a statistician. How does bagging work? Bagging works the following. You want to build T classifiers, and actually it's a Metalearning algorithm. Meta, like 1 level higher than a learning algorithm. You can plug in any classifier or regression model, whatever you want. It's above that level. You just plug in whatever. You want to build T models. How do you do that? You have your training data X. And what you do is now you take a Bootstrap sample. What does it mean to take a Bootstrap sample? Your sample your training data has n points. That means you draw n samples out of your training data, but you always replace them. That means you draw n samples, but it can be that you get some of the samples several times and others you don't draw because it's random. So it's sampling with replacement. So it's basically a re-weighting of the data set. Some instances you will see a couple of times, so it gives higher weights to these instances. Others you will not see at all. You give lower weight to it. So this is what you do. You draw a Bootstrap sample. Then you train your algorithm on it, whatever it is. You do this T times, so it basically prolongs your training time by a factor of T. And your final classifier is just the sign, in the case of a binary classification, of the sum. So it's a majority vote, an unweighted majority vote. Super simple. How does it create diversity? With a random selection of the data point that basically resemble a re-weighting of your sample. Sometimes you emphasize this part by sampling more from there. Sometimes you emphasize more this part. Of course, there's no being behind that emphasizes here and there. This is controlled just by randomness. But in the end, this is what the algorithm does. Each member of the ensemble looks at the data set from a different perspective, at a different reweighted version, reweighted by resampling. And that actually creates a very diverse ensemble that works very well in practice. This is already 50% of the ingredients for random forests. If you take this method, plug in for the algorithm and decision tree, this is already 50% of the idea of random forests. The rest, other 50%, you can find on the one-pager in the appendix. Good. How complicated is it to implement that? Super simple. I mean, let's assume we have a library with which we can do the resampling already. And it's almost less lines of code than the pseudocode here. So this is really remarkably simple to implement, and it works remarkably well. Good. So far for the introduction on ensembles. What we will do now is, I think we'll make a break and continue at 1:45.